We are in section 7.3, logarithmic functions and their graphs. First, we define what a log function is, how to graph it, and then you evaluate elementary log expressions, then talk about common and natural logarithms. Next slide. Okay. Definition. Let x be greater than 0, b is greater than 0, and not equal to 1. Okay, it's important it's not equal to 1, otherwise it'll be trivial. Then b raised to the y equal to x is equivalent to saying that y is the exponent, basically, of x, so that, of the base b, so that when you raise b to the y, you get x. So when you're evaluating the logarithm of x to the base b, you're just saying that if I raise b to the y, I get x. Okay? Examples. Let's just take a few examples here. Let's say 2 cubed we know is 8. So that's equivalent to saying that if I take the log of 8 to the base 2, then it's equal to 3, because 3 is the exponent that I raised the base 2 to get 8. Okay, give you another example. Say 3 squared we know is equal to 9. So if you write that in logarithmic form, you're saying that if I take the log of 9 with the base 3, then that is equal to 2. Because why? If I raise 3 to 2 to the power 2, I get 9, which is equal to 9. Okay, so the logarithmic form is the log of whatever is the result of raising b to a power y. Okay, so the log of x to the base b is equal to y, meaning b raised to the y is equal to x. So we're saying basically when you're answering the question of what is the logarithm of an expression, your answer would be it's an exponent. Okay, write exercise 1. Write the following equations or exponential equations in logarithmic form. So again, how do we do that? Okay, this is equivalent to saying that, okay, you've got the base 5 raised to the third power and you get 125. So if I take the log of 125 to the base 5, then I get 3. Why? Because 5 raised to the third power is equal to 125. Okay, let's look at this second example, letter B. Alright, what is the result of 7 raising it to the negative 2? It's 1 over 49. So that means if I take the logarithm of 1 over 49 to what base? To the base 7. Okay, that's your 7. Then we say it's equal to negative 2. Why? Because if I take 7 and raise it to the negative 2, I'll get 1 over 49. Okay, how about this one? This is the same as saying 16 raised to a half is equal to 4. So what is it equivalent to in log? You're saying that if I take the log of what? Well, I raised the base 16. So if I take the log of 4 to the base 16, okay, it's equal to 1/2. Why? Because 16 raised to a half, you get 4. Because why? When you say 16 raised to a half is the same as taking the square root of 16, and the square root of 16 is equal to 4. So please, the best way to understand logarithm is to practice. Okay? Get as many exercises as you can. You can find that online of how to convert from exponential form to logarithmic form, and vice versa. Okay, see, here is the opposite direction. So now we're asked to write each log equation here in exponential form. Again, remember these are the exponents. So how do we rewrite that? So this is equivalent to saying that if I take the base b and I raise it to the second power, I get 64. Okay, now here the logarithm of 81 to the base 3 is y. Is equivalent to saying that if I take the base 3, raise it to, what is this? The exponent y, I get 81. Similarly, for the letter C, what's the base? 5. What did I raise it to? To the exponent 6, I get x. Again, the key here is practice. What you can do is take all these and rewrite this in in logarithmic expression, and see if you get the same expressions on the left. All right, how do we graph logarithmic functions? Now remember, the logarithmic and exponential functions, they are inverses of each other. So if I take the graph of y is equal to 2 to the x, remember it's this curve right here, okay, and reflect it about the diagonal, what do I get? I get the logarithmic function. Okay, so they are inverses of each other. So take y equal to 2 to the x. Then how do we do inverses? Remember, we interchange the x and the y and solve for y, right? So if I have, so to get the inverse of y is equal to 2 to the x, first thing we do is we interchange the x and the y. So interchange, we get x is equal to 2 to the y. Solving for y is the same as writing it in logarithmic. So we say y is the exponent that I raise, okay, the base 2 to get x. So the log of x to the base 2. See, that is now your function right here, okay? So if we interchange the ordered pairs, so what are the important ordered pairs if you have y is equal to 2 to the x? Well, always we have 0, 1. Because why? 2 to the 0 is 1. And then when x is 1, y is 2. That's another ordered pair. If x is 2, y is 4. Okay? So all these ordered pairs, we're going to interchange them. So this ordered pair is 1, 2, right? This ordered pair is 2, 4. So now interchange those ordered pairs. So what do you get? You'll get 1, 0, right? And then here, instead of 1, 2, you get 2, 1. Again, interchange the ordered pairs here. You'll get 4, 2. Why? Because what is the log of 4 to the base 2? It's equal to 2. Okay, what is the log of 1 to the base 2? It's 0, because 2 raised to the 0 is equal to 1. Okay, so that's the behavior of the logarithm. It's just the inverse. They're inverses of each other. So really, you just interchange those ordered pairs. Okay, now what about the graph of when the base is between 0 and 1? Then you see that it was a decreasing function. It's a decreasing function, and so the logarithm is just a reflection about the diagonal. Then you have, this is the log of x to the base 1/2. It's a decreasing function as well. Okay. Oh, let's go back to the previous slide just to remind you that the domain, remember, the domain of y is equal to 2 to the x, a set of real numbers, and the range is from 0 to infinity. See that? Okay, so if we interchange those ordered pairs, this becomes the domain of its inverse. There you go. So I take all these elements and put it here. So if you notice that the domain of the logarithm is from 0 to infinity, and the range is the real set of real numbers, which means we cannot take the logarithm of 0 or negative. Okay, any number less than or equal to 0, you can't get its logarithm. Because why? It's the result of taking the base to an exponent, and whenever you take the base to an exponent, it's always greater than or equal to 0. So whenever you evaluate the logarithm of something, it's got to be greater than 0. Okay, so here's an example. Here's just a generic graph of a function where the base a is greater than 1, so it's increasing, and when the base is between 0 and 1, it's decreasing, kind of like just the same as the exponential. Okay, and notice that what are the important ordered pairs we look for in a logarithm? It's 1 over a and negative 1, 1, 0, and a 1. Why? Well, let's see. Okay, suppose your a is 2. Okay, suppose your a is 2. So everything here becomes 2. So that's 2. And that's 1/2. Okay, let's see if that's the case. What is the log of 2 to the base 2? Well, what did I raise to get 2? 1. What is the log of 1 to the base 2? What did I, again, you ask yourself, it's like playing Jeopardy. What did I raise to get 1? It's 0 because 2 to the 0 is 1. Okay, take this 1/2. What is the log of 1/2 to the base 2? Well, what did I raise to get 1/2? Negative 1. So these are key ordered pairs that you want to look for when you're looking at logarithms. And same thing with bases between 0 and 1. Okay?